consider a problem that you may encounter in Java. You may recall in Java that there is the variable type int, and then there's the variable type called long. And both of these are actually for integers. The difference was that this is 32 bits, and this one over here is 64 bits. And the problem that I want to talk about here, it's actually pretty simple, is what happens if I try to assign, what happens if I come over here and I say int x, and I say long y, and I do some calculations over here, and I try to say something like x is equal to y, or I try and come over here and say y is equal to x. In other words, what happens when I try, in this situation here, I'm trying to take something that's 64 bits long and put it into 32 bits. In this situation over here, I'm trying to take something that's 32 bits and put it into 64 bits. Well, sometimes you can do it and sometimes you can't. And the question is there any way that the computer can conveniently figure out if there's a problem or not? Now, in talking about this problem, I find it a little bit difficult to write out 32 bits and 64 bits. So what I want to assume is I want to assume that we're working with 8-bit signed integers and also 16-bit signed integers. And I just want to talk about what are the issues about converting from one to the other. Okay, well, let's consider the following number. Suppose I were to just look at this number right over here. 2, 3, 4, 5, 6, 7, 8. Now I'm considering this as an 8-bit signed number. And we can see that the leading bit is a 0. So we know that this is a positive number. And in fact, we know that this thing over here is just the number 3 in base 10. It's a 1 plus a 2. And I think you can see that to convert this into a 16-bit signed number is actually pretty simple. All I have to do is stick another 8 zeros in front of it. 1, 2, 3, 4, 5, 6, 7, 8. And then I need to go 1, 2, 3, 4, 5, 6, 7, 8. So in taking the 8-bit signed integer, a positive one, and converting it into a 16-bit signed integer, it seems like all I needed to do was tack a bunch of zeros on front of it. Okay, that was easy. Well, let's consider a negative number. Suppose I had minus 3 base 10. Well, first of all, I don't know how to write that. So what I've got to do is I'm going to come over here and I'm going to take the 2's complement and I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to add a 1 to it. And that is now 1, 0, 1, 1, 1, 2, 3, 4. Okay, so this number over here is minus 3 in as an 8-bit signed integer. Well, what is minus 3 as a 16-bit signed integer? Well, again, I'm going to take the 2's complement of this, 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to add a 1 to it. I flipped all the bits here. Now I add 1. And I can see that this is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Well, look at this. Here is minus 3 as an 8-bit signed integer. And here it is as a 16-bit signed integer. And you can see that when the number was positive, all I needed to do was add 8 zeros. When the number's negative, all I needed to do was add 8 ones. Well, we've got a name for this. Basically, notice that in this case, we took this bit right here, and we just propagated it to the left. And likewise, what we did over here is we just took this bit right here, and we propagated it to the left. You can't see that other 1 anymore. Okay? This is what's referred to as sign propagation. So basically what this means is that if you have a smaller signed integer and you want to convert it to a larger signed integer, all you need to do is take the leftmost bit and keep repeating it until you get the number of bits that you need. Okay? But then now, suppose I had a 16-bit signed integer, and it looked like the following. And now what I want to do is I want to take this and I want to convert it into an 8-bit integer. Well, the first thing I recognize is if I go 1, 2, 3, 4, 5, 6, 7, 8, if I just chop it off at that point there, you can see that I'm very clearly losing information. And in fact, you can, if you think about it, you're going to see that you will lose information if these 9 bits here don't match. So in other words, this over here would give me an error if I tried to convert this into an 8-bit number. On the other hand, this we can see over here that these match this. So I can safely convert this into 8 bits. And how do I do it? I just chop it right over there. Okay, I hope that was easy. So far we've been restricting our talk to integers in the kind of data we can store on a computer. We've talked about the unsigned and the signed integers. There are some other things that we need to consider as well. A very important one, of course, are characters. It might be the case that I want to store somebody's name in memory. Our good friend Joe Smith, maybe Joe Smith's address. And Joe lives in Ipsy. And the point is that the computer needs some mechanism via which it can store characters. Now remember, inside of the computer, everything is zeros and ones. So what we need to do is we need to come up with a way of storing all of these characters. Now what I'm going to do here is tell you a story that is almost factually correct, not quite. And you're going to hear me tell the same story in class. Here's the idea. When people were sitting around developing computers back in the 1940s, they recognized the fact that they needed some way of representing symbols. And what they did is they made a very big table of all the symbols that they might need to print out. So they recognized that they were going to have the letters. So they had A and B and C, and they went all the way up to Z. By the way, those are capital letters. They recognize that they're going to need lowercase letters all the way up to a little z. They're going to need other things in here. For example, they're going to need the integers as individual characters all the way up to 9. They recognized that they were going to need punctuation, a period, an exclamation point. They made this list. Okay, it was a very long list. And what they started to do, so this list kind of looked like this. And they said, what we're going to do, so someplace in here is A, B, someplace way down here is little a, little b. And they started numbering the list. And like computer scientists always do, they started off at 0, and it went 0, 1, 2, and it kept going. By the time they got to capital A, it was at 65, and then it was at 66, and it kept going like this. And then they got to the little letters, and then they got to all sorts of other goofy symbols. And here's where I'm going to tell a little bit of a lie. The list really ended somewhere over here, but I'm going to say it came all the way down here and it went up to 255. Now the reason why I said 255 is that works out very nicely here. 255, of course, equals 2 to the 8th minus 1, which means that if I wanted to, I could store all of these in 8 bits. Okay, like that. Any one of these characters could be stored in 8 bits, and that's the reason we have this 8 bits is equal to 1 byte. So for example, if I wanted to store the letter A in 8 bits, remember this is 1, 2, 4, 8, 16, 32, 64, 128. Well, 65 is 64 plus a 1. Everything else is a 0. So if I were to look at this right here, and I would say to you, that's a character. What character is it? You would come over and look in this table and go, oh, that's the letter A. If I were to say to you, oh, no, I'm sorry, I made a mistake. That's actually a signed 8-bit number, then you would say it's 65. That's why I say that you can never just look at a bunch of bits and know that what they are. You have to know what sort of representation they're giving you. So for example, if I looked in memory and I saw this, this would, and I would say to you, those are characters. This would be A, B, C. Okay. This table over here is very frequently referred to as the ASCII table. ASCII stands for something that I can never remember, the American something or other. There are a couple of interesting things to note about the ASCII table. In the ASCII table, the lowercase letters come after the uppercase letters. So in most programming languages, if I'm comparing this to, say, this, that's a true statement. But what's really kind of weird is that this is true. An uppercase Z is less than a lowercase a. It turns out that the digits are up here before the letters. Okay. And it's something that in your spare time you might want to go ahead and take a look at these. Okay, so that is the ASCII. The very last thing to talk about in this chapter is what's called hex, which is short for hexadecimal. Okay, and hex is really base 16. And the problem we have is how do we represent 16 different things? In other words, in base 10 we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we start repeating the digits. We would come over here to 10. In hex, I need 16 different symbols, so I start using letters. A, B, C, D, E, and F. And you can think of these as that, yeah, A really corresponds to 10, 11, 12, 13, 14, 15. And there are a couple of different ways to think about it. For example, if I were to come over here and write 3EA, and I were to say to you, what is that? Or suppose I were to say, it's an integer. What integer is it? Well, if you remember like we did in binary, this is A times 16 to the 0. This over here is E times 16 to the first. And this over here is 3 times 16 squared. Well, let's figure these things out. First of all, 16 to the 0 is just 1. A is a 10, so this is 10. This over here, E, is 14 times 16 to the first. And over here, 16 squared is 256. This is times 3. And now what I have to do is I have to add all of these up. Well, this number over here, that's 8 carry the 1, 6 carry the 1 is 7. Okay. 16 times 14, can you do that in your head? Well, 16 times 16 is 256. And I have to subtract 32. So 256. So that's a 4, 2, 2. And then I add 10. And that is equal to, I don't know, 768, 224, 10. That's a 2, carry the 1, 6, 7, 8, 9, 10. That's 0, carry the 1. That's 102. So that's 1002 in base 10. Okay? That's not, what you're seeing over here, that's really not the reason we use hexadecimal. The reason why we use hexadecimal is very frequently we're writing binary numbers. We write these binary numbers and when they get really long like this, it's really easy to make a mistake. It's easy to make a 1 a 0 or a 0 or a 1. So what we do is we rewrite them, and it turns out that converting between hexadecimal and binary is really simple. All you need to do is you start over here on the right side, and you break things up into groups of 4. So there's 4 bits. Here's 1, 2, 3. Here's 4 bits. Here's 1, 2, 3. Here's 4 bits. Here's 1, 2, 3, 4. Here's 1, 2, 3, 4. And over here I have 2. So what I'm going to do is I'm just going to add 2 more to it. And it turns out that, remember, if I have 4 bits, okay, 4 bits as an unsigned number gets me from 0 to 15. Or if I'm thinking in hex, it gets me from 0 to F. So in other words, if I come over here and I look at this over here, this is a 0, this is a 1 plus a 2 plus a 4 plus an 8. There's just a 2 here. This over here is a 2 plus a 4. That's a 6. Remember, that's 1, 2, 4, 8. 1, 2, 4, 8. So this is 8 plus 2 is 10. Remember, 10 is an A. I come over here, this is a 2 plus a 4, this is a 6. This is a 2 plus a 4 plus an 8. 8 plus 4 is 12, 13, 14. That's an E. And this over here is a 3. So over here I have 1, 2, 3, 4, 5, 6. Over here I've got 24 bits. Over here I've got 6 hex digits. This, of course, is much easier to write. So the way to convert back and forth is if you think of each hexadecimal digit as being 4 bits. Okay, it's going to be a number between 0 and 15. Then what you can do is, suppose I have a number that looks like this. Suppose I have 8F A3. Well, the 8 is 1, 0, 0, 0. The F is a 1, 1, 1, 1. The A, remember A is 10. 10 is 8 plus 2. That's 1, 0, 1, 0. And the 3 is going to be 0, 0, 1, 1. So this is taking a hex number and converting it into a binary number. So quickly now, here's an interesting thing. Suppose I'm talking about 16-bit signed ints. And I want to know, and I'm going to say that it's given in hex. And the question is it negative? So if these are hex digits here, okay, 4 of them, that's 16 bits, what happens is I have to look at this expanded, and if I look at that expanded, remember that's 4 bits. It doesn't matter what this is, but what I have to have over here, if it's a negative number, that's got to be a 1. Well, if that's got to be a 1, that says that this hex digit has to be at least an 8. So if I were looking at this as being a 16-bit signed integer, I see an 8 there and I go, it's a negative number. If I see this, it's a negative number. If I see this, I know it's a positive number. Okay.